Okay, I'd like to welcome everyone to the seminar, and a reminder that the meeting is being recorded. If you have questions during the talk, feel free to unmute yourself and ask the question. Otherwise, we ask that you stay muted. You can also raise your hand electronically if you prefer, or put a question in the chat, whatever works for you. So our speaker today is Rosa Sena-Dias from the Instituto Superior Técnico in Portugal, speaking on minimal Lagrangian tori and toric manifolds.
Okay, so let me start by thanking the organizers. I'm very happy to speak here. So everything I'm going to say is joint work with Gonçalo Oliveira. And I'm going to be talking about a minimal Lagrangian tori in toric manifolds. Okay, so before I start, so minimal submanifolds are sort of a very old subject in mathematics. They were introduced a long time ago in the around the 1750s by Euler and by Lagrange, who first studied them as submanifolds, I think, in R3. So nowadays, of course, they are a hot topic, and they're the object of a lot of great work. But in a sense, they remain elusive because they're subtle objects. And so we have few examples apart from the obvious ones and some other hard ones. But essentially, we don't have that many examples of minimal submanifolds. Okay, as far as Lagrangian submanifolds are concerned, it's kind of the opposite in a sense. There are plenty of Lagrangian in symplectic manifolds. There's even a famous quote, "Everything is a Lagrangian," which is due to Weinstein. Everything is a Lagrangian manifold. I'll talk a bit more about this, but you know, Lagrangians are easy to find. Despite that, they're also the object of a lot of attention, but rather than finding examples, people want to sort of classify them or compare them. They want to organize them. So one of the reasons why they're so important is that they're essential tools in defining our strongest symplectic invariants. So, for instance, they're the objects in what's called the Fukaya category, which is sort of the starting point of a lot of invariants for symplectic manifolds these days. And part of the reason why they are so important is that they give good boundary conditions for pseudo-holomorphic curves. And as that, they're also important in defining Floer homology. Okay, so my title involves minimal and Lagrangian, and so does it make sense to put the two notions together? Is it interesting? Has it been discussed before? And in fact, so to my knowledge, I think that the minimal Lagrangians study started with a paper, which it's a 1996 paper of Stromingers, Zaslow, and Yau. And the paper is on mirror symmetry. And the idea is that they want to explain how mirror symmetry would go in the setting of six-dimensional collab Yaus. It doesn't matter at all if you're not familiar with that setting. But they describe mirror symmetry in terms of minimal Lagrangian fibrations. So this is not where I'm going, but I think it's an important motivation for studying minimal Lagrangians. So let me just roughly say what they say. I think that a way to phrase their paper is that on a Calabi Yau of 6 real dimension, there should be a large subset which is given as a fibration whose fibers are minimal Lagrangian tori. Okay, and then this is kind of not that important to me, but once you have that those fibrations, once you have that family of minimal Lagrangian tori, you can find the dual of each tori, whatever that means, and you construct another fibration by minimal Lagrangian tori, which gives you a mirror for this Calabi Yau. Okay, and I think that at this point, minimal Lagrangians came under the spotlight. They became interesting, and also it became possible, or it was sort of conjectured that they would exist, and in fact lots would exist because they're describing a fibration. Okay, so does the question make sense? Can you mix the two notions? Well, to discuss minimal Lagrangians, you need to be at the intersection of Riemannian geometry and symplectic geometry, because the notions belong. Minimal belongs in Riemannian and Lagrangian belongs in symplectic. Okay, so because I'm speaking at the intersection of these two areas, I sort of feel like I have to give a bit of background in each, because I don't know if I'm speaking to symplectic geometers or Riemannian geometers. And so perhaps I will bore you, and perhaps I'll be talking about things that you know better than I do. But so from Riemannian geometry, the only thing I really need is the definition of a minimal submanifold. You've probably seen it, but just to make sure. So suppose you have a Riemannian manifold and you have a submanifold, which I'm encoding through this map. So I keep track of the map. So a submanifold is said to be minimal if it is stationary for the volume among variations of the map. So that's simply, so a variation, in the last line of this definition, I've written down a variation. A variation is a family of maps starting at the initial submanifold, and such that all of the maps, all of the phi t's are themselves submanifolds. And being stationary for volume just means that the derivative of the volume along this family needs to be zero, at zero, okay? So the way that, this is, as I've said, a very old definition, and people have calculated the derivative of this volume. And it turns out that it can be expressed in terms of curvature through the mean curvature. So being minimal is equivalent to having a zero mean curvature. I'm not going to use that at all, but it's a very important fact, and it's key to the study of minimal submanifolds. So I felt I had to write this down. Okay, so I think the most confusing thing about minimal submanifolds, I have to say, is their name. So even though they're called minimal submanifolds, they don't necessarily minimize volume. I think we call them minimal submanifolds because we honor the historic name, but they don't necessarily minimize volume. There's lots of examples where they don't. And they even have a notion of index and nullity, just as other critical points of normal functions do. So, and of course, these are defined in terms of the second derivative. Okay, even if you're not a Riemannian geometer, and even if you've never worked with minimal submanifolds, you're sure to have encountered them because there are some special examples. For instance, geodesics are one-dimensional minimal submanifolds. If you're a complex geometer or an algebraic geometer, you've certainly encountered them because, well, complex submanifolds in complex manifolds are always minimal. And if you're a symplectic geometer, then you've also encountered them because pseudo-holomorphic curves are minimal. Okay, so I've said that these minimal submanifolds are elusive and that we have few examples. Let me mention sort of a few existing constructions which I think are important and sort of maybe, you know, I want to discuss them here. I guess that one of them, which holds only in 3 dimensions, is really an existence result due to Meeks and Yao. They show that every isotopy class of a surface has a minimizer, which happens to be a minimal submanifold as well. Another important construction or another important set of constructions are what's called gluing constructions. And these were sort of started by Palais. There was lots of work around this after him, and other people have used his ideas. But the idea here is that if you have 2 minimal submanifolds that maybe intersect a certain way, sometimes you can glue them in the sense that you can build a smooth submanifold out of the union. Okay, the other very recent or recent set of constructions comes from applying min-max, and those are due to Marx and Neves, and their method is extremely powerful, and they are able to construct many examples or to prove existence for many examples. The only downside of their method is, or I mean, maybe it's not a downside, it is what it is, but they often don't control the topology of what they construct. They construct minimal things, but they don't know what they are. Okay, so let me move towards symplectic geometry. Again, if you're an expert in symplectic geometry, I will bore you, but if you're not, then I feel like I have to say something. So suppose you have a manifold. It's symplectic when it carries a 2 form, which needs to be closed and nowhere vanishing. So this condition here is called non-degeneracy. And so the first condition is a PDE sort of condition. The second is an algebraic condition. And the mix between the two is sort of what makes the subject interesting. For instance, it's given a manifold unless for some obvious reason, like its H2 is 0. We don't know whether it's symplectic or not. It's a hard problem in general to decide whether a symplectic manifold whether a manifold carries a symplectic structure. Okay, so symplectic geometry is like Riemannian geometry, a rich subject, but the only thing I really need to say about it is really I need the definition of a Lagrangian. So a Lagrangian submanifold is one to which the symplectic form restricts to 0. So I can phrase it like this, but I could also phrase it as it's a submanifold such that the restriction of the form vanishes. They're always half-dimensional. Okay, and sort of to comment on everything is a Lagrangian quotation. So one way to interpret it is any manifold can be interpreted as a Lagrangian because any manifold, any x, it's called x here, can be seen as the 0 section in its cotangent bundle. So the cotangent bundles are the most famous symplectic manifolds. They have started the subject. Any cotangent bundle carries a canonical symplectic structure. And of course, the submanifold can be seen as the 0 section, and it's always a Lagrangian, and it's sort of the prototypical the prototypical example of Lagrangian. Okay, so as in many areas of geometry, group actions have been really important in studying symplectic manifolds. And just as Riemannian geometers are interested in isometric group actions, symplectic geometers are interested in actions by symplectomorphisms. So a symplectomorphism means a diffeomorphism which preserves the two form. It pulls back the two form to itself. Okay, and those are of course used to study symplectic manifolds. But in fact, symplectic geometers are often interested in a special type of symplectic action called a Hamiltonian action. Okay, so I'm going to take the next slide to define a Hamiltonian action. I think I wouldn't normally do it, but I think you're the right audience for this. And it sort of gives me an excuse to define an important object, which is the moment map. Okay, so, well, suppose you have a symplectic manifold with a group action. We say that the action is a Hamiltonian if, well, first of all, it needs to be an action by symplectomorphisms, which is just what I've said here. Every element in the group preserves the two form. And then the special thing is the following. So for every element in the Lie algebra of the group, there is an induced vector field, which I'm calling xc. Because there is a two form, you can contract the vector field with the two form, and it's very easy to show using Cartan's magical formula that this one form above which I'm waving the little hand is closed. And so for a Hamiltonian action, you want it to be exact. Okay, you want this form to be d of something, which depends on the vector field. But in fact, you want slightly more, and this is where it gets a bit more complicated. So every time you're able to do this, to define a primitive for the one form determined by the vector field, you're able to define a map from the manifold to the dual of the Lie algebra. And the map is simply given, well, if it's defined on the dual of the Lie algebra, it means I can pair it with a vector field on the Lie algebra. And once I do, I should get a function, and this is simply the f psi. Okay. Now there's a choice involved in the f psi because I only have the derivatives, and so they're defined up to a constant. And being Hamiltonian makes it so that you have to be able to choose this so that this map here is equivariant. So equivariant with respect to what? Well, there's a natural action on n. It's the action we're discussing, and the action in the dual of the Lie algebra is the adjoint action. Okay. So the moment that the mu map here is really important in symplectic geometry and in what I'm going to say. It's called the moment map of the Hamiltonian action. So in fact, if you found the definition confusing, or if you can't remember it, you should think about it as an action is Hamiltonian if you can define a moment map, really. Okay, so I'm actually going to be speaking about a subset of, a special subset of symplectic geometry. I'm working in Kähler geometry because I've also said this before a little bit. So the minimal condition needs a metric. The Lagrangian condition needs a symplectic form. So if I want to discuss both, I need to be on a manifold which is symplectic and Riemannian, and I will ask it to be symplectic and Riemannian in a compatible way. So I'm going to be working on Kähler manifolds. So compatible means that there's a complex structure which relates the metric and the symplectic two forms. So the metric is a symmetric tensor. The symplectic form is a two form. It's anti-symmetric, so they could never be equal. And compatibility means that they must be related to a structure J. So something, well, in principle, I wouldn't have to ask for it to be integrable, but I do. I want to ask this J to correspond to a complex structure. So the manifolds I'm working with are complex manifolds. Okay, so toric geometry, which is my own setting for this work. So a toric manifold is a symplectic manifold with an effective Hamiltonian action of a torus. Okay, we say that toric manifolds are maximally symmetric because whenever you have the action of, well, whenever you have a Hamiltonian action of a torus on a symplectic manifold, then the dimension of the torus is at most half the dimension of the manifold, because the fibres of this action need to be, well, isotropic. It doesn't matter. But I couldn't have a Tn+1 torus acting here. Okay, and when I'm able to choose the torus to be of maximal dimension, that is half of the dimension, I call the manifold toric. So because the action is Hamiltonian, there is a moment map, and it takes values in the dual of the Lie algebra of the torus, which can be identified with Rn. I just have to pick a basis for this dual to do that. And it's really the moment map image, so that's going to play an important role for me, and it doesn't in general in toric geometry. And it's called the moment polytope. And why is it called the moment polytope and not just the moment map image? Because it is a polytope. And this is sort of it's a hard result. It's highly non-trivial. It was this moment map image is a convex polytope. It's due to Atiyah and Bott and independently to Gilman and Sternberg. Okay, what's more, this moment map image determines the symplectic toric manifolds. It determines, what I mean by determine is it determines up to equivariant symplectomorphism, let's say. So it determines the manifold, the symplectic form, but also the torus action. This is a theorem due to Dalzin. It's also an interesting result. Okay, because of this, symplectic geometry of toric manifolds often turns into Euclidean geometry of convex polytopes. And there are many examples of problems that are problems in symplectic geometry that turn into something much simpler and much more elementary. Sometimes it's not simpler, but it's more elementary in the Euclidean geometry of the moment polytope. Okay, so I mean, you've all encountered toric manifold before. There are examples, there are important examples. So the first one is sort of the baby example, is the two-sphere. So think of the two-sphere on sitting inside S3. The round metric and its usual complex structure make it so that it's a symplectic manifold. And it has an S1 action by rotations, right? S1 acts by rotations in the usual way. Here's the picture. It's meant to represent rotations in S2. Now the moment map is easy to calculate here. It's just the height function. You could easily do it if I gave you the formula for the Fubini-Studi metric. And so if I want to determine the moment polytope, it's just where the height takes it's just where the height takes values. So it's an interval. So if you normalize it like I do, you get -1,1, but you could get any interval, any closed interval, depending on how you normalize. Okay, it's certainly a convex polytope. Okay, the second example, you've probably also encountered. And I want to treat it in detail because it's going to be sort of the leitmotif in the talk. I'm going to keep it around to illustrate things I say. So it's the projective space. I'm choosing CP2 because it's more concrete. So CP2 is toric, and let me say a little bit more about that. CP2 has a T2 action. So T2 I'm writing is S1 times S1. It has many, but they're all equivalent. And so I'm going to choose one like this. So these Z0, Z1, and Z2 are homogeneous coordinates. And I'm just going to have T2 act on Z1 and Z2. Okay, again, it's a choice, but they're all equivalent. So because also CP2 is symplectic, there's the Fubini-Studi metric. It arises from the Fubini-Studi form. Now, if you calculate the moment map, you get this. It's well defined. I mean, it doesn't depend on the choice for homogeneous coordinates. And now if you want to calculate the moment map image, you have to decide where this takes values. So it's clear that each component is positive. So the moment polytope will be in the first quadrant. And if you sum these two coordinates, you see that the denominator is Z0 squared plus the numerator. So it's bigger. And so the sum is smaller than 1. And in fact, you can very easily convince yourself the moment polytope is this. So it's a right angle triangle, which is also isosceles. Okay, so I want to discuss the fibers of the moment map because they're going to be important for me. So I'm going to talk about this example in more detail. So you can think of CP2 as a quotient of S3 as well by just doing the usual thing. You normalize homogeneous coordinates so that the norm is 1. And then once you do that, the moment map becomes this. Okay, and I'm going to discuss the fibers of this map. Okay, so in blue, I've drawn the edges of the moment map of CP2 and the moment map image of CP2, sorry. And suppose you have a point XY in green here in the interior of that polytope. What is the fiber through the moment map of that? That's the question that I'm asking. Okay, so because x is the norm of Z1 squared, then the Z1 coordinate has to have norm x. Okay, so it has x as a norm and then an argument. The Z2 coordinate, just the same, its norm is y and then an argument. And now the Z0 coordinate, you can also deduce its norm because of the restriction of that I've written down here, that it's a normalization. In principle, I would have an argument here as well, but I can divide throughout. And then I can just assume that Z0 is real, okay? So why do I want to write it like this? Because, so this is the fiber of a point in the interior, this one. And it's pretty clear when I write it like this, that it's a T2, because here's an S1, here's another one, okay? Now, once I move my XY to the boundary of the moment polytope, what happens to the fiber? So I'm calculating now the fiber above a point, which is of this form, 0y. And the Z1 needs to be 0 because x is 0. And I'm left with y, with Z2, whose norm is y. And again, I can normalize Z0 to be real. And then you see that these fibers are now in S1. So the fibers above this edge here are S1s. How about what happens for 0, 0? Well, if you're asking the norm of Z1 to be 0, then Z1 must be 0, then Z2 must be 0. There's only one point which gets mapped to 0, 0 through the moment map. Okay. So what happens is the fibers over the interior are tori, the fibers of the interior of the facets are circles, and the fibers over vertices are points. Okay. And also, and this is going to be important to me, you can see through this that, well, the action over the points in the interior is free. There are no fixed points. The action over the edges has an isotropy of dimension 1, and the vertices correspond to fixed points of the action. Okay, so in general, the moment polytope of a toric manifold is a special type of polytope. It's always an intersection of half planes. You can always write it like this, where these LKs are the defining functions of the facets. And they are, in fact, even more special than that, because these new Ks, which are really the normals to the facets, satisfy a certain relation between each other. Okay, another important thing which I want to say, well, so it's going to be important for me. Something else I want you to know and to remember about toric manifolds is that they are complex tori compactifications. So toric manifolds have a definition through complex geometry, which I'm not giving, and it would be easier to see this if I had given that. But I can still say something that will kind of convince you of this. So as I've said, the toric manifolds can be seen as compactifications of complex tori. And why is that? So because the torus acts freely at points over the interior of the moment polytope, then any toric manifold contains an open dense subset, which is just the pre-image of the moment map of the interior, the pre-image via the moment map of the interior of the moment polytope, which is a complex torus. This M0 is just the subset of M where the torus action has no isotropy or just trivial isotropy. Why is it a complex torus? Well, okay, so over that interior of the moment map, the mu is a fibration, okay? And because the interior of the moment map is the contraction, then this fibration is trivial, and M0 is a product of the torus with the polytope. And the torus with the polytope is a complex torus, just in the same way, yeah, exactly. Just in the same way as C star can be thought of as S1 across an open interval. Okay, so the M, which is the toric manifold, contains an open dense subset, which is a complex torus. So I'll say it's a compactification. One of the reasons why I want to say this, why I want you to think of this so badly, is that this actually helps me introduce what are called action angle coordinates. These are just extremely convenient coordinates. They are sort of the reason why we can do everything so explicitly in toric geometry. They come from the identification where the little hand here is. They are just defined on this M0, this open dense subset. And the theta, the angle coordinate is the coordinate on the torus factor, and the x coordinate is really just the moment map, but it's the coordinates on the polytope, on the interior of the polytope. Okay. Okay. So now, one of the reasons why these coordinates are so good is that they make the symplectic form standard. They are what's called Darboux coordinates. Okay, you can write the form in these coordinates as is there. Okay, So this is a picture of the compactification story. This is again CP2, and its polytope has dark blue edges. So here is a fiber above the interior. Suppose I move towards an edge along this pink path here. Then above each point in the pink line, I'm going to have a torus, but it's going to be a different torus. And as I reach the boundary, I will no longer get a torus, I will get a circle. And what happens along this path is that a loop, which is non-trivial, which gives a non-trivial element in homology, gets contracted, and the torus becomes an S1. Now the same thing happens if I move along the pale blue line here, but a different loop gets contracted. It's the blue loop here, the longer one. It's a different element in H1. And if I went towards the third edge along this yellow line, the same thing would happen. And the interesting thing is that the normals here give the direction of the loop that gets contracted. So the normals to the facets sort of encode the isotropy. So above the edges, I get a similar picture, but one dimension lower. What happens is, think of just this edge, for instance. The preimage of a point on the edge is a circle, but as I vary along the edge, the circle is varying as well. And it gets smaller until I get to a vertex, which is an edge for the interval. And there the circle shrinks to a point. And so if you see this picture here, just above the edge, it's an S2. Okay, so there should be an S2 sitting in site CP2 as the preimage of the edge. And if you think of the expression for the moment map, being on this edge is just having Z1 equals to 0, which is a hyperplane section in CP2. So it's an S2. Okay. So it's a way of seeing the geometry of CP2 with toric eyes. Okay, so, but I've said that to talk about minimal Lagrangians, I need to be in the toric setting. I need to be in the Kähler setting. And I've presented toric manifolds as symplectic manifolds. There hasn't been a metric so far. And so why is there a metric? Well, this is a theorem. It's really a theorem of Abreu, but it builds on work of Gilman. What they show is that toric symplectic manifolds, in fact, admit many Kähler metrics. That is, they admit metrics compatible with the symplectic form, which are also invariant with respect to the torus action. And in fact, we have a very precise understanding of what these metrics are. So they're parametrized by a smooth convex function satisfying certain conditions in the interior of the moment polytope. Okay, so such a function is called a symplectic potential, and these play an important role in understanding toric manifolds. So one of the conditions on the metric, on the symplectic potential, I said that it satisfies two. One of them is that even though U is not a smooth function on the closure of the polytope, its behavior at the boundary is prescribed by this blue function here, okay? So this function is continuous, the blue function is continuous on the boundary of the polytope, but not smooth. So, sorry, the LKs are the functions that define the boundary of the polytope, okay? And there is another condition, but I don't need it, so I'm going to just not talk about it. So a symplectic potential defines a metric in this very concrete way. So the Uij's here are the entries of the Hessian of U, which is convex, if you remember. And so this, so the U's with the upper indices are the entries of the inverse, and this is what the metric is. One of the reasons why I want to write it down, I'm actually going to use this later, but look at this. If you look at this formula, it's obvious that this defines a metric on M0 because it's positive definite. I mean, convexity of U implies that both this part and this part are positive definite. But what's not obvious from this formula is that this closes up to the boundary to give a metric on the whole polytope. And that's a consequence of the condition of asymptotic behavior on the boundary. That's not obvious, and it's part of Miguel and Victor's work. Okay, so for CP2, just to make this concrete again, I've said that the Fubini-Studi metric is Kähler and T2 invariant, so it must have a symplectic potential. So I need to tell you what it is, and it's actually just the blue function itself on the polytope, which is this triangle. Okay, so if you remember the L1 for CP2, so the edges are the ones that were in the drawings before. So this is just the Li log Li. Okay, so I'm finally in the position where I can state our results. So again, this is work with all of this is work with Gonçalo. And so here's part of what we've shown. Suppose you have a toric manifold with a toric metric. Here's the whole information, the toric manifold, the metric, and the action. You then have a moment map. What we show is that there is, among the fibers of mu, a minimal submanifold. And we've also shown that if the Ricci curvature of the metric is positive, then this fiber is the unique minimal submanifold among fibers. And we have also shown that if you give yourself any finite set or discrete set in the interior of the moment polytope, then there is a Toric Kähler metric whose fibers above that set are minimal. That is, you can prescribe minimal fibers in a sense. Okay, so using the same techniques, we've proved other things. We've proved results in the non-compact case. We've proved things on stability, that is the nullity. And we have a result which maybe I'll have time to discuss on Hamiltonian stationary fibers. And we also have something on the mean curvature flow. But rather than stating our results, I think I would rather discuss the methods, because I think that the metrics are sort of, I think, interesting in other settings for people who are working with symmetries and group actions. So, but before I do that, I had promised to show the existence of a minimal Lagrangian torus, and I've just talked about minimal so far. So I should convince you that the minimal fiber is actually a Lagrangian torus. But that's easy, actually, with what I've said. Perhaps you figured that out. Why is it a torus first? Well, the moment map is just X. So a fiber of it is just given by the set where the thetas vary, and they vary in the torus. So the fibers are tori. Why are they Lagrangian? Well, that just comes from this formula. Because if I make, well, the fibers, okay, so why are the fibers Lagrangian? If you make X a constant, which is what taking a fiber means, then this here vanishes, becomes 0, so the form vanishes. So here they are. Here is where the minimal Lagrangian tori come from. The only thing I need to convince you of is that I can find a minimal fiber. Okay, then tori and Lagrangian will follow for free. Okay, I want to mention before I move on, I want to mention some related results. So first of all, since the 96 paper of Strominger, Zaslow, and Yao, there were really deep and important works of, in particular, Shane and Wolfson, related to existence of minimal Lagrangians. But there were actually also things in the setting of toric geometry. So there's a paper of 2001 by Goldstein, who showed that for a toric manifold with a Kähler-Einstein metric, there is a unique minimal Lagrangian. So we recover his results, but I mean, there are very few Kähler-Einstein metrics. So he's talking about a very restrictive case. Of course, he was interested in Kähler-Einstein because it's related to Calabi-Yau and because of mirror symmetry. But another related result is due to Pacini in 2003. And he also works in the Kähler-Einstein setting, but he works for non-abelian groups. And so his work is really interesting. He generalizes Goldstein to non-abelian, to other groups. Okay, so let me start sort of discussing a little bit of what's behind this. And what's behind is a principle of Palais, which is called the Principle of Symmetric Criticality. Let me write it down for you. So it's really an important thing, and once you work with group actions, you've probably encountered it. So the principle goes as follows. Suppose you have a smooth map on a manifold, and there's a group acting on the manifold. Then the idea is that the critical points which of the functional or the function which are fixed by the group action are just critical points of the manifold restricted to the fixed points. Okay, so here MG denotes the fixed point set as I think as usual. And let me rephrase this principle. So what this says is that given a fixed point for the G action, if for some reason you're able to prove that the derivative of the function at that point is zero, just along invariant directions, just along tangent directions to the fixed point set, then that's enough to prove that the whole derivative vanishes, okay? Of course, I mean, there are many directions which are, or there are potentially many directions which are not tangent to the fixed point set. So this is more the second condition is more demanding, but the principle says that it's enough to verify the first. Okay, so this principle is interesting when M is an infinite dimensional manifold. And for us, the setting we need is we want F to be the volume and M to be the set of submanifolds. And already you see that how is the set of submanifolds a manifold? You could get into trouble. But there is a Tn action here. There is a Tn action on the manifold, and so the set of submanifolds inherits that. Okay, so in a 79 paper, Palais showed that this principle of symmetric criticality doesn't always hold, but he wanted to use it. So he proved, he gave some general conditions under which it does hold. Okay, and so the question is, do they hold in our setting? And that's been checked by Xiang Lawson. In fact, they prove that it holds, but they don't use Palais conditions at all. They do it directly, and it's surprisingly simple. And Xiang Lawson's theorem is really the main ingredient. So let me write it down precisely. And it's more general than what we need. So it's really an interesting result. Suppose you have it's easy, but it's interesting. Suppose you have, and they've used it, and other people have used it. So suppose you have a manifold with a Lie group action, and suppose that you find a G invariant submanifold which is stationary for volume just among invariant variations, then it's minimal. Okay, this is a rephrasing of the Palais principle for this setting precisely. Okay, if you assume that, then our theorem actually is easy in some sense. So the only thing, well, I need to convince you first that invariant variations of fibers are nearby fibers. But you can think of that, well, think of the image of the variation. It contains some point. And because I want invariant variations, then it needs to contain the whole fiber above that point. And it's a variation, so it's of the same dimension, so it must be the fiber. Okay, it's sort of, this is roughly how the argument goes. So Tn invariant variations of the fibers are fibers. So a fiber is minimal if it is stationary for volume among fibers. Okay, so I need to calculate the volume of fibers and find critical points for that. And for that, so here's the metric. This is the formula I wrote down before. So if you restrict to the fiber, you drop this because the fiber is x equals to 0. And if you look at this expression, this is a flat metric on the torus. So all of these fibers are flat tori. Of course, the metrics still vary with x, but they're all flat. And I can just calculate their volume. It's the determinant of the inverse of the Hessian. And so I need critical points for this determinant of the inverse of the Hessian. Okay, the critical points of this function here, which is a function on the moment polytope, will give me minimal fibers. So does it have critical points? Okay, and this is where the compactification picture is helpful. As we approach the boundary, the fibers collapse, if you remember in the case of CP2, but this is always true. They collapse in the sense that they become lower dimensional because the Tn action acquires isotropy. So they collapse, therefore their volume tends to 0. And so the volume is bounded. It extends to the whole polytope, and it's bounded from below. And so it has a maximum, and this maximum is the fiber we're claiming is minimal. Okay, so for CP2, here it is. So here's CP2. Here is it's a symplectic potential. I've calculated the Hessian for you. It's a very easy calculation. I've calculated the determinant of the inverse of the Hessian. Here it is. This is the volume of the fibers. And please notice that it vanishes as it should on the boundaries. And to find minimal submanifolds, I just need to find the critical points of this, which is a very elementary calculation. Both of these need to vanish. And so if you carry out, this is what you get. And what I like about this is that this gives sort of a famous minimal submanifolds of CP2 with just super elementary calculus. This is the Clifford torus. So it's what's called the Clifford torus. It's the torus above this point. It's known to be a minimal submanifold in CP2. Okay, so about the prescribing part, I think there's something interesting to this too. Well, so the claim was that any set of fibers can be seen as a set of minimal submanifolds. To prove that, we would need to prove that you can prescribe the critical points because if you of this function, because if you remember, the critical points of this function are minimal fibers. So instead of prescribing the critical points, we actually prescribe the function on a proper subset of the interior, and it gives the Monge-Ampère equation. Okay, prescribing this function here is a Monge-Ampère equation, and there's lots known about those, and we just used a result of Caffarelli, Nirenberg, and Sprock to ensure existence of the U and therefore of the metric. Okay, So let's see, maybe I still have time to discuss these Hamiltonian stationary fibers result. So the idea here is that in the Lagrangian setting, you are, this has been thought of a lot. You are often interested in manifolds that are stationary for just what's called Hamiltonian variation. So this sort of variation that encapsulates the symplectic geometry. So let me just quickly say a variation of submanifolds is Hamiltonian if the vector field it generates is exact in the sense that this one form is exact, just as in the definition for a Hamiltonian action that I was given before. Okay, this is how the variation generates a vector field in the usual way. It's just a vector field along the image of the submanifold. Of course, it's not tangent to the submanifold. Otherwise, this one form would be zero because the form vanishes on the Lagrangians. So a Lagrangian is said to be Hamiltonian stationary if it's stationary just for variations among if it's stationary for volume just among the special type of Hamiltonian variations. And of course, there are less Hamiltonian variations than variations. So in principle, there would be more Hamiltonian stationary submanifolds. And again, the two sorts of minimality have been compared, and there's results of Shane and Wolfson here too. And there are deep results. So in principle, Hamiltonian stationary is a lot less restrictive. And what we show with Gonçalo is that in the toric setting, it is a lot less restrictive because all interior fibers, absolutely all of them, are Hamiltonian stationary, even though just sometimes just one is minimal. Okay, so this in fact generalizes a result that is due to Irene Jean-Renian Rollin, who proved the same thing for just the Gilman metric. The Gilman metric is the metric whose symplectic potential is given by the blue function. It doesn't really matter. It's some famous metric on toric manifolds. Okay. Okay, so I don't know if I still have a minute. I don't know if I do. I can talk.
You can take a minute. Go ahead.
I can talk about open problems. I mean, maybe just one or two. I think that our methods sort of maybe still have a lot more to give, and I don't think we've exhausted what one can do. One problem which I find interesting, I haven't thought about it, but one feels like could give something interesting is one could use this to maybe find minimal submanifolds as graphs. So there's a lot of work in the area of minimal submanifolds for finding graphs, and I think one could try to look for graphs over Lagrangians over the Lagrangian fibers and try to see if there are any minimal ones. The other problem, which I think is maybe worth thinking of, is that of prescribing the fibers exactly. So we've said that there's a metric with certain fibers which are minimal. I wonder if there is a metric with exactly such fibers minimal, and that would mean solving Monge-Ampère equation with a singular behavior at the boundary. I mean, there's a lot on that, but there's so much that I don't know if there is what I need. I couldn't figure that out. Okay, well, I mean, there's more, but maybe I should stop here. And thank you for your attention. Just say thank you.
Thank you for a beautiful talk. Really nice results. Are there questions?
I have a question. It's very nice talk. I was wondering if that's if the following thing is true, at least sometimes. That can you hear me?
Yes, I can hear you.
Sorry. So if you look at the orbits of the group action on G, you also have the distribution orthogonal to that. And does it happen for some of these metrics that distribution is integrable?
Yes. There's a special one which is called the real submanifold, which is kind of a copy of the polytope. There's an involution on these manifolds, which comes from conjugation. They can be seen, and there's a complex description of them. So there's a conjugation which gives an involution. And so there's a real submanifold. So this is like RP2 on CP2.
Okay, like a section of the Hamiltonian function.
Yes.
So then this moment map reduces to a function on this submanifold invariant in the Weyl group.
Yes. It's like a finite covering of the polytope. You can see it as a finite covering of the polytope.
So that happens for one of these for a special Kähler metric?
No, it's true for all of them.
True for all of them. Okay.
It's true for all of them. And it's true for all toric manifolds. They all have this real submanifold, and it's always minimal because it's totally geodesic.
Right. Is that helpful to reduce things to this to the submanifold?
Sorry?
Is it helpful to reduce discussions to the submanifolds since it's a smooth manifold?
Yes,
without boundary?
Yes. So for instance, I think one could wonder, is there a graph over that? Or could you write down the equation for a graph over that that's a minimal submanifold? The problem is like RP2. It's not orientable in general. So
does that matter?
Maybe
so
not.
Like the volume function certainly becomes a function on the submanifold, right?
Yes.
Its critical points would be minimal.
Yes.
And I assume the differential equation would then be a differential equation on a smooth manifold, as opposed to a manifold with boundary, which might be more convenient.
Yes. So in terms of finding a graph, do you mean?
No, in order to study this differential equation, instead of on the polytope, you could do it on the smooth submanifold.
Yes, but for us it was very easy because the function we just wanted the critical points of this function, right. And the function is 0 on the boundary.
Okay, I see. Mm-hmm. Sure, that's true. Okay.
Yeah, for other settings, yes. But this way of thinking about toric manifolds is very interesting. You can think of the real manifold as a covering of the polytope, and it sometimes solves the problem that the polytope is open or that has boundary. Yes.
I see. So these are special cases of what are called polar actions, or group actions, where you have this property. It's something I studied before, so I was wondering if these are special examples of polar actions. So they are. It's interesting. Thank you.
Are there other questions? If not, well, thank you again for your great talk.